So good afternoon, everyone. It's now time to start the web security session. My name is Aurore Fass. I'm a faculty at CISPA, and I will be your session chair. So in this session, we have 4 super interesting talks related to various aspects of web security. And it's now my pleasure to introduce the first speaker, Jam, who is a PhD candidate at Northeastern University and works in systems and web security. So now he's going to present their approach to fingerprint servers in a multi-layer architecture. So James, the floor is yours.
Thank you so much for the introduction. So I'm Cem Topçuoğlu. I'm a PhD candidate at Northeastern University, and today I'm going to talk about the multi-layer web server fingerprinting. So what is web server fingerprinting? So it's basically a task where we try to find the server that the target runs on. So we use it for many cases, actually. We use it for reconnaissance. We use it for security management, such as like asset discovery, vulnerability tracking. We use it for attack surface discovery. And currently, we use the tools such as like Nmap and Nessus, and these tools are implemented the state-of-the-art version of the web server fingerprinting. However, the state-of-the-art actually makes an assumption. So the assumption over here is that we have a monolithic web. So it assumes that we have only one single server in the communication path. However, as you know, this is not true today. So actually, we have more tangled web today. So we have like multiple proxies in the communication path. For example, we might have something like CDN, like Cloudflare, and then we can just like proxy our communication to the origin server. So, for example, Nginx. So the state-of-the-art actually cannot work with this setup. So now we have a problem, actually. OK, so I will first go over how the fingerprinting works, and then I will tell why it's not working on the current topologies. So currently, what we do is just like this. We are picking a request. This can be something like unconventional or invalid request. And then we are sending this request to the target server. At this point, we expect a response. And we previously also test on these servers. And we are sending some requests. And we also collect the responses back from them. And we know the subtle differences, actually. So for example, over here, we can see that ATS is kind of like returning a different response line when we compare the other ones. So by collecting these subtle differences, we are detecting one of the servers. For example, let's say the response that we got is similar something to the third one. So we might think it's an Nginx server. However, as I mentioned, we have these multiple proxies. So actually, there are some problems with that. So actually, we are not sure if the server that we detected is Nginx or not. And we don't know if there are additional layers. So like it might be 2 layers, 3 layers, we don't know. And even though there is an Nginx server, we don't know which one is Nginx. So if it is in the first layer, if it's in the second layer. So the main problem over here is that while we are sending a request by and these requests are just like forwarded by these different servers, they are making some transformations on these requests, both in the upstream and the downstream. So it affects our responses as well. So it changes and it adds some new headers, some new characters, etc. So it actually confuses us. So we make some misclassifications, and we are confused at all. So to solve this, our approach is Untangle. We use HTTP processing discrepancies to fingerprint literally everything. So we fingerprint them both in their type and order. So we use these processing discrepancies, and you might ask, why are these processing discrepancies over there? So it's basically, while these people, like web server implementers, implementing their servers, they are looking at the RFCs, and RFCs are open to interpretation. And they are making some implementation and design choices, and they end up actually with different versions of these web servers. So instead of explaining an abstract methodology, we will go over a case study to explain our methodology. However, before delving into that, we need to make an assumption that we have this global picture of all the servers in this world. So let's assume we know all the servers, all the web servers, and let's say we have like unlimitless number of requests that we can just like send to these servers. So this will be our behavior repository. So this behavior repository actually includes these requests and corresponding responses for each server to that request. So if we look at it on the right-hand side, we can see that, for example, for request 1, Apache will return an error. ATS will return an error. And like for all of them, for example, for request 1 will return an error. So we have this global picture. Also, we know if Apache returns an error, we know the specific error response as well. So we know what will be the error code. We know what will be the error response code. So we will use this, utilize this in our methodology. So let's start with our case study. Let's say we have this 3 layers over here. So Cloudflare forwards to Squid, Squid forwards to Tomcat, and we want to fingerprint the target. So we utilize Untangle over here. And as a first step, Untangle just like goes and tries to find a request such that all of the servers return an error. So idea over here is that if we want to detect layer 1, we make sure that it won't be forwarded from the first layer. So like we want the first layer to return an error. So we look at our behavior repository. So when we look at it, we can see that request 1 is a suitable request. So we have picked that request, and we are sending it to the target. So over here, Cloudflare will return an error to us, and we will just match the error response that we got with the error responses that we already collected. So for example, for Cloudflare, we knew all the headers, all the response lines, etc., everything about it, and we will just like do a similarity match. So eventually, we will detect it as Cloudflare. So right now, we know the first layer. OK, so what is the next step? So again, using the same logic, actually, we will just like go for a request, like returns an error for all servers, except this time we want Cloudflare forwards it, because like we already detected that layer. So we again look at our behavior repository, and we see that request 2 is a suitable request for this, and we pick that, we send it. This time, Squid returns an error. So we again get the error response, we vet the error response, we do a similarity match, and we find out it's the Squid server. Again, in the third step, similar logic. We want this time Cloudflare and Squid forwarded, and all others will return an error. So again, we have that request in our behavior repository. So we send it, and we decide it's a Tomcat server. So overall, our methodology worked like this. However, like there are some more details. I'll just like go into that one right now. So Untangle in real life, however, might not be working like this, because we made an assumption over there that we have a complete like behavior repository. So we assumed that we knew everything about these servers. We were able to find everything about these servers. However, in real life, there might not be discrepancies in between these two servers. And even if there are, we might not be able to find them. However, there's a good news. Untangle also can work with these situations as well. So we can work with these situations, and we can present complete. So what I mean complete is we can find both the order and the type of it, or we can present partially ordered results. So we can, for example, find the first layer, and we can only detect the second and third layers' names, but we might not comment on their orderings. So for details of this, please refer to the paper. So like we have much more detailed methodology, actually, but because of time constraints, I couldn't go into details over here. And creating the behavior repository. So how we do it, we actually pick common web servers, load balancers, CDNs, 13 in total, and we differentially fuzz them. So we mutate our HTTP requests, and we send these requests to the servers. We collect the responses, which eventually created our behavior repository, and this actually fits our tool. And in our evaluation, we did two different things. So in the first step, we did an in-lab experiment. So we deployed 3-layer topologies, and we also tested Untangle on all the viable permutations of these like 13 servers. So this was like scientific one, actually. So we know the ground truth over here. So these are the results, actually. In total, we had 756 permutations, and Untangle was able to find the 100% of the first layer, 90.3% of the second layer, and 50.7% of the third layer. So you might ask why there's a decrease when we go into the deeper layers. So the reason is that since our behavior repository is not complete, for some cases, we couldn't find the suitable requests. So we were not able to find for those cases, actually. And if you see a number over there, for example, for layer 3, it says 383. So that means that for 383 permutations, we were able to find the layer 1, layer 2, and layer 3. And it might not be a fair comparison with Untangle, because like Nmap works in this like single layer setting, but like that was our comparison point, because like it implements the state of the art. We actually compared with Mmap. So Mmap actually performed like this. It's just like it was able to detect 59.5% of the layer 1 servers. And for the rest of it, for the rest 40%, for example, for the 20%, it couldn't find anything. For the remaining 10%, it did some misclassifications. So when we look at Untangle, we can see that like it actually performs really well. We have an idea about these like layers, and we can see the ordering as well. And the final experiment is testing in the wild. So this was kind of like a fun experiment, and because we didn't have the ground truth, so we just like tested on the first layer. We didn't go into deeper layers over here. So, and we did, like we collected Trancos 10K sites and tested on them. So we can see that in general, there's a consensus in between Untangle, Unmap, and the Nmap over here. So we saw also some differences, some like huge differences in between them as well. And for those cases, we did a manual analysis, and we saw that actually Untangle performs really well on those analyses as well. So we are kind of confident that Untangle actually works very well, and like it can work in the wild as well. So as a conclusion, we present a novel and actually a first way to fingerprint multi-layered web servers. So we also made it available our source code. So please go and download it, play with it. And it will be a pleasure for us to like hear about your experiences, because like we don't have the ground truth, but like you might have for your own servers. And if you can report back to us, like you can just like proceed. And yeah, thank you so much for listening. Do you have questions?
Thank you so much for the very great talk. So do you have any questions? And so please state your name and affiliation first.
Hi, Robert McLaughlin from UC Santa Barbara. I was wondering, in your evaluation, when you're talking about the percentage of applications in the layer 3 that you could classify correctly, what about the ones that you couldn't classify correctly? Do you just simply say we don't know, or are they misclassified as something else?
For some cases, we had some misclassifications, but they were like really, really low. So like mainly the ones that we couldn't find is just like happened because like we lacked the required requests from our behavior repository.
Okay, thank you.
Thank you.
Hey, Manuel Egele, Boston University. Awesome talk, thank you. So I was wondering, for your behavior repository, you had 13 different HTTP-capable servers that you tested and you extracted your behaviors from. So that's good. I would assume that the configuration for each and every server can potentially affect as well the request or the responses rather that you see from them. So to what extent did you explore that configuration space within those 13 different?
All right, yeah, great question actually. So like we didn't test different configurations, so we tested them in their default configuration. But actually, like, it's a great idea, of course, to like explore that part as well. So like, I would like to also see how they differ when I change their like configurations. Is there upcoming? Okay, sorry, I didn't see.
Oh, yeah, Eric Pauly, Wisconsin-Madison. I was also curious about the sort of behavior library. And this is maybe a little speculative, but do you see the current behavior library as being somewhat exhaustive, or is there potential to sort of expand it and improve performance?
Sorry, like, what do you mean current behavior libraries?
Well, you're characterizing based on this, on distinguishing different types of behavior of the servers.
Yeah,
right?
exactly.
Do you foresee expanding the types of behaviors that you would characterize in these servers to improve detection rates, or do you think it's sort of played out all the different behaviors that you could characterize?
I think I couldn't understand your question. So, so we have this behavior repository, and like, are you asking the generation phase or like the usage of it?
Do you think that you could improve performance by expanding the space of behaviors of each of these servers that you characterize?
Yeah, we can expand, of course. Like, we can expand, but like, we can do that thing as well. Also, we can just like improve our fuzzer as well. So then we can just like generate different type of HTTP requests, and like that might lead some different discrepancies as well.
Thanks.
Zubair Shafiq, UC Davis. Quick question. Is your approach capable of handling non-deterministic behaviors? You send the same request. Sometimes the answer is one thing. Sometimes the answer is the other thing, but there is a pattern to it.
So like, we don't handle those cases. So like, we expect that they behave like in a deterministic way.
Thank you.
So we have time for maybe one or two more questions. But in the meantime, I can ask you a quick question. So I was wondering, so when you have like these three layers, and you said at the third layer, you can't always like have a request that would be forwarded by the first two layers and generate an error on the third layer. Isn't that an indication in itself of the type of server you may have in the third layer?
Like, for example, when I have the first and the second layer, and like...
Yeah, because if you can't find like a request that would be forwarded by the first and second layer and have an error on the third layer, can't you restrict the possibilities of what the third server could be?
Yeah, actually, like we kind of actually limit those ones. Like, so when we see over there in our behavior repository, two of these servers forwards, we actually don't consider them for the third layer. So we kind of like eliminate those ones. We don't consider. We don't do a similarity bench with those ones. We do with the remaining ones actually.
Okay, cool. And if there are no more questions, let's thank the speaker again.
Thanks so much.